All right, hi everyone. I'm very happy to be here. So my name is Behmard. I'm a postdoc at the Center for Computational Astrophysics / Flatiron. And today I'm going to be talking about some work that we recently wrapped up on measuring detailed chemical compositions for a large sample of M-dwarfs in the Sloan Digital Sky Survey. Okay, so if we're interested in planets, why should we care about M-dwarfs? So a couple of reasons. The first is that M-dwarfs are the most common type of star in the galaxy. They actually compose about 70% of stars in the solar neighborhood. M-dwarfs are also the best stars for detecting and characterizing planets, including Earth analogs. And this is because M-dwarfs are relatively low in mass and small in size compared to solar-like or sun-like stars. So this means that planets that orbit around M-dwarfs are going to induce stronger transit and radial velocity signals. And because M-dwarfs are smaller in size, their habitable zones are also going to lie closer into the host star. So it's going to be much easier to detect planets in these habitable zones, even if these planets are small and rocky, like Earth. So for all these reasons, M-dwarfs are super popular targets for exoplanet surveys. So for example, TESS has targeted tons of M-dwarfs, and when I just looked through the JWST database, I found about 100 M-dwarfs targeted in cycles 1 through 3. So we're really interested in measuring chemical compositions for M-dwarfs. And that's because in general, if we want to understand planets and their formation pathways, it's really important to constrain the chemical compositions of host stars. So how this can shake out is, for example, we can use host star compositions to break degeneracies between planet bulk densities and their actual chemical compositions. So for example, we can consider the TRAPPIST-1 system. And if we assign different amounts or abundances of elements like, say, iron, magnesium, or silicon to the M-dwarf host star, that's actually going to change the compositions of the planets hosted by TRAPPIST-1. It's going to dictate whether they're, say, more iron-dominated or silicate-dominated in their compositions. And then, for example, if we're interested in initial planet formation locations and migration histories, it's also really valuable to have knowledge of the host star composition because we can compare the ratios of certain abundances in planetary atmospheres versus in those of the host star. For example, ratios like carbon to oxygen, which can tell us whether planets formed within or beyond certain characteristic ice lines in the protoplanetary disk. But there is a problem. So it's a long-standing challenge to measure the chemical compositions of M-dwarfs because they're very cool in temperature. And this basically facilitates the formation of lots of different types of molecules. And these molecules make it super hard for us to actually measure the chemistry of M-dwarfs. And this is because molecules basically create these dense forests of spectral lines in the optical and near-infrared regions of spectra. So here in this plot, I'm showing 3 examples of synthetic spectra that are going down in temperature from top to bottom. The spectrum at the bottom is in the M-dwarf temperature regime, and you can see that it looks much more complex because of the presence of all of these molecular lines. And in general, we don't have a good handle on these molecular lines in terms of their opacities, their line strengths, and other properties. And for this reason, it's really hard for us to construct accurate physical stellar models of M-dwarf atmospheres. And physical stellar models is the classical method that we use to measure host star compositions or stellar compositions in general. They're pretty good for solar-like stars or sun-like stars, but they really struggle in this M-dwarf regime. So what we did to measure chemical compositions in our sample is we just bypassed using physical stellar models altogether, and instead we used the Cannon. So Isabel Angelo introduced the Cannon to you. I'm going to talk about it a bit more. So the Cannon is essentially a data-driven framework that allows you to infer abundances and parameters for stars given just their spectra. It's totally independent of physical models. It's named in honor of Annie Jump Cannon, who was an astronomer and computer at Harvard College Observatory and who led the efforts to establish the first and still current stellar classification system. So in a nutshell, the Cannon works by basically utilizing a training set of stars and their spectra that have well-determined labels, and then the Cannon basically uses that training set to construct flux models that can be applied to other stars to determine their labels. And labels here is just a machine learning terminology way of describing different physical parameters and abundances in stars that you might be interested in, like temperature, log G, different chemical species. And in general, the Cannon can be used to infer whatever abundances or parameters you wanted to, as long as you have that information in your training set. So more on that. So the Cannon works via a 2-step process. So in the first step, or the training step, we basically use a training set of stars and their spectra, And in this case, for the training stars, we know their like labels for different abundances and parameters super well. Like we trust them, we think they're very accurate. And then we use that set of spectra to basically construct a bunch of flux models where there's one flux model at every pixel in the wavelength range of our spectra. And then in the second step, or the test step, we apply that set of flux models to the spectra of stars where we want to determine their abundance and parameter labels. So in this way, we can characterize them. So we drew our sample of M dwarfs from SDSS-5, which is the current phase of the Sloan Digital Sky Survey. So SDSS-5 is essentially an all-sky spectroscopic survey that's taking optical and near-infrared spectra for over 6 million objects in our galaxy and beyond. It's composed of 3 sub-surveys. This is Black Hole Mapper, Local Volume Mapper, and Milky Way Mapper. And we're interested in Milky Way Mapper. So Milky Way Mapper is all-sky spectroscopic. It's in the H-band, so near-infrared, and it's pretty high resolution, so R of about 22,500. And Milky Way Mapper and SDSS in general have their own built-in abundance measurement pipeline called ASPCAP. ASPCAP relies on physical stellar models, so it's pretty good for solar-like or sun-like stars, which have temperatures above 4,500 Kelvin, but that's not going to fit for M dwarfs. But we could still use it to construct a training set of M dwarfs for our purposes. So because ASPCAP is reliable for solar-like stars, what we did is we looked for binary systems in Milky Way Mapper, where one of the stars is an FGK dwarf or solar-like star, and the other star is an M dwarf. And because these binary companions are gravitationally bound, we can assume that they formed in the same parent molecular cloud and thus formed from the same material. And so they should be roughly chemically homogeneous. So then what we did is we basically tagged the M dwarfs with the ASPCAP chemical abundances of the solar-like companion, and that formed the basis of our training set. So we found about 80 pairs like this in Milky Way Mapper of FGK M dwarfs, and that's basically what we trained the cannon on. Okay, so then once we had our training set, we wanted to verify its validity. So we kind of wanted to check that it's okay to assign the M dwarfs the abundance labels of their FGK companions. So we did this by running leave one out cross-validation tests, which is basically we took one M dwarf out of our training set, then we ran the cannon on the remaining N-1 stars to construct a flux model, then we applied that flux model to the star that we took out. And we did this for every M dwarf in our training set. So the results are shown in these panels here, where each of the panels corresponds to a different element. The y-axis corresponds to our inferred abundances for the M dwarfs, and the x-axis are the abundances for the FGK companions. So we want to see one-to-one trends, because that's going to indicate that the FGK companion labels correspond pretty well to the M dwarf spectra. So you can see that that's pretty much what we see here. So all of the RMS differences between our inferred labels for the M dwarfs versus the FGK companion labels are given in the upper left corners of the plots. You can see they range from 0.1 to 0.17 dex, so that's pretty good in general. And all of the panels here, as I said, correspond to different elements. I'm only showing ones that are pretty interesting for planet formation studies here, so iron, magnesium, silicon, carbon, oxygen, titanium. But our model actually infers further abundances beyond this. So we also have aluminum, nitrogen, calcium, chromium, and nickel. And a lot of these elements are very interesting for galactic archaeology studies as well, beyond planet formation. Okay, so then we wanted to run a few more tests to verify that the M dwarf abundances we get from our model are pretty high quality. So one of the tests we did is we wanted to make sure that we can reproduce some known reported abundances of M dwarfs in the Hyades cluster. So our results are shown here. So there are some studies that basically used boutique stellar models to infer or to measure oxygen and bulk metallicity for M dwarfs and Hyades. And in these plots here, we're showing our inferred oxygen and iron values on the y-axis versus the reported values, and you can see everything kind of fits pretty well together. It's all kind of clumped together as opposed to stretched out along the linear trend, because all of these M dwarfs come from Hyades, so they're all naturally pretty chemically homogeneous, so everything's kind of stuck together. But we're doing a pretty good job of reproducing these values. So the RMS scatter between our inferred values versus the reported is 0.05 dex for both elements. So after we were pretty happy with our M dwarf model, we went ahead and applied it to all of the M dwarfs in SDSS-5 that have reliable, high-quality spectra. And this is about 17,000 M dwarfs. And after we did that, we wanted to run one more sanity check, which is we wanted to make sure that our M dwarf metallicities reproduce expected metallicity tracks from stellar evolution. So what we're showing here in the plot on the left is our results, and this is basically like a Kiel diagram of log G versus temperature. The metallicities that we get from our model are given by the colors, and you can kind of see the tracks that we expect, which are delineated more carefully in the plot on the right, which is from another paper that showed these tracks also in colors for a big sample of M-dwarfs. You can see they match up pretty well, so looks good. Okay, so just to summarize, so we use the canon to basically infer a bunch of M-dwarf abundances for many different elements. This has resulted in a catalog of about 17,000 M-dwarfs from SDSS5, and this paper was recently accepted, so this catalog should be out soon. And in general, these approaches of like using data-driven tools to characterize stars is, I think, very valuable now that we're in the era of large spectroscopic surveys like SDSS, because data-driven tools like the canon are super fast. So I think that this catalog can be used for examining star and planet formation with these M-dwarf chemical compositions, and I also cross-matched this catalog with the catalog of confirmed exoplanets recently that's given in the plot right here. So we have, it's about like 90 confirmed planets. We have like planet radii versus orbital period, and the M-dwarf host stars are colored by the metallicities we infer. So you can already see some interesting stuff. Like for the giant planet host stars, they do appear to be more metal-rich, which is what we would expect given the planet metallicity correlation. And you already see like some potential trends with planet orbital period as well. So I think there's like a lot of interesting science that can be done with this. There's also 5 JWST host stars in the sample as well. There might be more, but I need to check more carefully. So very excited to see what the community does with this catalog, and that's all I have. So thank you. Happy to take any questions.
Awesome. Thanks, Ida, for a great talk. Time for a couple questions. We'll start with one from online.
Yeah, so we have one question from online. Does this work include any rare earth elements?
No, so it's just the ones I showed. So it's like carbon, oxygen, nitrogen, a bunch of refractories. So I think it's like 11 altogether. Yeah.
Great talk. I was curious, like whether/how you folded in the stellar rotation of your training sample or V sin I or anything like that.
Yeah, I actually didn't. I think there were like a few M-dwarfs in the training set that I determined to be like fast rotators, so I just removed those because they kind of like messed up the results. But I didn't actually use V sin I or any like rotation measurements. I think at some point I had some sort of broadening parameter as a label, but I found that it didn't improve the results.
Hi, thanks, great talk. Tim Benning, Sydney University. People who talk about machine learning talk about the importance of having a large training set. So 80 obviously isn't huge. Is there a chance to expand it, for example, finding more binaries or maybe even some open clusters which have M-dwarf spectra?
I'm sorry, can you repeat the second part of that?
Expanding the training set with maybe more binaries or even open clusters if they have M-dwarf spectra.
Yeah, like what are the prospects of expanding
Yeah.
the training set? I think that prospects are potentially good because I think that if we like utilize Gaia astrometric parameters, we can potentially identify more like bound pairs in general, and then we can like look for those in SDSS5 to see if we can get abundances. So I definitely think that's a good route to go down. Yeah, it's true that like we like will definitely benefit from a bigger training set, but more than that, it's not really like the size, it's more like the like parameter space that it spans. But yeah, I think that there are good prospects for that.
Great talk and exciting work. I was curious to know if this technique is sensitive to the molecular bandheads of like TIO, VO. Do you get good abundances for this?
I don't. That would be really exciting though. So we would need like a set of labeled M-dwarfs like with those molecular abundances. I think like David Correa is maybe doing some work on that, but right now we don't in general as a community have like that sort of sample, but it's an exciting route to go down for sure.
Awesome. Time for one last question while we maybe get the next speaker up.
Yeah, very interesting talk. I just have a question. Did you kind of go back and use this to infer which features perhaps in existing stellar models are actually reliable to be able to infer those for the planets, the stars that are not in your sample?
Are you asking, like, are there certain spectral features in mDOR
Yes.
spectra that, right. Yes, I would encourage you to check out some papers by Diogo Suoto et al. And like some of the folks that are affiliated with, or some of the folks who collaborate with Katya Kunha. You talk to me later, I can like send you those links. But yes, in general, people are finding that there are some mDOR spectral features that we trust a great deal. They're like trying to compile boutique line lists, so there's a lot of energy in that direction.
Amazing. Let's thank Ida one more time.